Hello, my name is Dr. Emil Svoboda, and I'm at a conference in Chicago, and I'm going to narrate my presentation called Can We Make Intraoral Cementation Safer? And we're at a conference of the American Academy of Implant Dentistry, Solving Dental Implant Dilemmas. I'd like to acknowledge the contribution of Milan Jovanovic, who's a registered dental technician. And this is two faces of Milan, one with a big beard and one without, but he certainly helps me create the physical realities of my designs that I'll display today in my presentation. And this is Vladimir Agranat. He's a PhD in fluid mechanics. And since I am not versed in that discipline, I've asked him to consult with me regarding the validity of my terms that I use for fluid dynamics as regards to intraoral cementation. Today I want to talk about treatment complications because they have many contributing factors that interact with each other. And some of them are patient related and some of them are industry related. And I would bring your attention to technology and its limitations, and that certainly accuracy costs money, and extreme accuracy costs a lot more money. And this is what the industry is faced with some of the parts that we are assembling in patients' mouths. And I'm going to mainly focus on the dentist-related complications that are created during the installation of prosthetics in the mouth. And certainly complications are bad for our patients and bad for business. Preventing technique-related complications. My talk will head through a number of different topics, including why we need to cement intraorally in the first place, how to make it safer, and then I want to discuss retrievability. And then I want to show how, using what we've learned in the safer cementation techniques, how we can apply that to making screw-in prosthesis installation safer as well. 4 significant reviews between 2013 and 2015 with thousands of dental implants showed that the peri-implant disease rates on the implant basis was about 45% of the implants that we place. And all these peri-implant disease situations require treatment from the dentist and cost money to the patient. And they found that whether the prosthesis was installed by a cement-in technique or a screw-in technique, that the complication rates were about the same. So the perceived implant dilemma is, should we cement our prosthetics in or screw our prosthetics in, and is there a difference? Certainly doing the same thing over and over again and expecting a different result is the definition of insanity, according to Albert Einstein. And we have to focus on what is really safer for the patient. So what is the problem with the screw-in installation? The laboratory, on the basis of the impressions, makes a model and then starts to create the prosthesis on the model and assembles the parts on the model. So when the dentist gets these parts, why do we have to adjust contacts, fit and occlusion when we're trying to install these in the mouth? And why do we have good days and bad days? The fit seems to be variable, and it's whether they're created from digital impressions or from physical impressions. So the problem is that with the screwed-in prosthesis is that it's assembled on an inaccurate model. The models we're able to create today are just inaccurate, and they have enough inaccuracy that this creates a problem. And model inaccuracy is difficult for the dentist to assess and to compensate for, and that's one of the problems. So how does that look? I've created some models, some diagrams. So here we have on the left, we have an abutment prosthesis complex that's joined together, and it's assembled on implant analogs on a model. And now if we want to transfer that to the mouth, we take it together as a unit and we want to put it into the mouth. And you see it's frozen together. It's joined together either by cement or actually by casting and porcelain on all these techniques, but it's joined together, and that's the point. And when we try to fit this in the mouth, well, if the model is a little bit inaccurate, say it's too big, then we have a hard time to make it seat properly. And and even tight contacts on one side or the other will tend to keep the prosthesis from sitting properly. So we create something called an implant abutment misfit, and this misfit is created at the level of the alveolar bone, deep in the subgingival space. And they're difficult to assess by the clinician, but they create problems, and they're also difficult to treat. And they create, as we're trying to screw the prosthesis abutment complex into the mouth, the inclines of the inside of the implant are put under tremendous pressure, and the screw, if the channels of the abutment and the implant are not lined up, will be on an angle that causes the screw to be bent as it's put into place. And so, and the amount of pressure that is caused by these two parts coming together can put a lot of pressure also on the supporting bone. So we have misfit of components, distortion of parts, possibly movement of parts, a weakened retaining screws, and on the biological side, we have stress on bone, and we're creating voids and the possibility of microbial invasion at the implant abutment interface. And the size of this macro gap or implant abutment misfit matters. And it matters because in the biological world, disease is expressed as a result of host resistance, size of the inoculum, and the virility of the pathogens that are in that inoculum. So size matters because size can house many more oral pathogens than when they're in a small number. So Dr. Scott Fromm from NYU, a periodontist, he just wrote in 2017 a paper about the dreaded macro gap. The dreaded macro gap has been discussed for many years, and especially between 1980 and I guess the middle of 1990, that's all we talked about. And then it sort of went quiet as if we had solved this problem, but we never really solved the problem. And it's nice to see Dr. Scott Fromm bring it up again. The dreaded macro gap is caused, he thinks, by inaccurate impression and model distortion. Well, I'd go further than that. I would say all of our impressions are inaccurate and all of our models are distorted, regardless whether it's digital or physical. And tight contacts, certainly, the second point, is certainly a problem. And tissue interferences, especially when you have mating surfaces between the abutment or crown and the implant that are flat, tissues can get pinched in these and prevent the prosthesis or the abutment from seating. And I've seen that clinically. So I agree with that. Yeah, precision costs money, and as fourth point, cheaper inaccurate parts. Well, that's a problem because accuracy costs money, and so cheaper parts, they don't have the tolerances or the accuracy, and they're clinicians sometimes go for them because they think everything is the same, but they're not. And I think probably the best way to get the most accurate parts is to look at the tolerances and perhaps maybe go from the authentic parts catalogs, because at least they take the responsibility to make sure that their parts are accurate. And this has become such a big problem that the government of Canada now has legislation that determines who can make that implant abutment junction, and it's based on the accuracy of that junction. So the government has actually had to step in because of that being a problem. Use of engaging abutments. Well, with multi-units, with many multi-units, it's difficult to use in gauging abutments because the implants are not exactly parallel, and you just can't install them. And so multi-unit abutments are often used. They don't engage or hold on the implant as well, but that's what's used for multi-units. This is what the sixth was an interesting point, is that he felt that trying to reinsert an abutment that has been previously misfit. And he's alluding to the fact that maybe the abutment is distorted now. And worse than that, maybe even the implant is distorted by that misfit. And I do believe he's on the right path here. And titanium is not such a hard metal, and so it can be distorted. And of course, he references his small, concise paper. He relates the macro gap to peri-implantitis, which is something we want to prevent or reduce. And he talks about screw fracture being a problem of this misfit. And I showed you a little mechanism by which that could be happening. Now, in another recent paper, Paulo Malo of All in 4 fame and his colleagues came up with a logarithm based on different risk factors that they had identified. And I read that paper, and certain things were kind of left out. But the history of periodontitis, we all recognize as being a risk factor. And how many people who have lost all their teeth really didn't have a little bit of periodontitis or in their history? Certainly, when there's sort of single missing teeth, those patients perhaps didn't have any periodontitis. But the ones that have lost them all, they certainly probably have. And then we go down to lack of passive fit or prosthetic loosening. And I would say in multi-units, this is a big problem, and I would say it probably occurs in 100% of the cases. And one of the interesting points was that when I went through his grid at the beginning, I used milled ceramics as my default. And in fact, that seems to have the least contribution to peri-implant disease because of its, I guess because of its accuracy. And porcelain bonded to metal frameworks seem to contribute significantly to peri-implant disease. And I would guess that was because those prostheses would not be as accurate as the milled counterparts. And we'll go on and discuss this a little bit further now. And in Paulo Malo and his colleagues' paper, these are the two pictures that they show to assess non-optimal screw joints. And I would say that his study probably was not set up for, and nor do I think that clinical practice x-rays are set up for determining macro gaps. One has to put a lot of things in place to really see these macro gaps because they're pretty small, and the resolution of our x-rays is around 25 microns. Bacteria are 1 micron in diameter, and so macro gaps, yeah, they probably fall below the resolution of most of our x-rays. And if we don't go really parallel or I mean perpendicular to the implant abutment joint, we're probably not going to see them. And certainly if we're taking panoramics like in this diagram here, and I've designated with the blue arrows, we would not see the misfits at these areas, and these abutment acrylic holding devices these are huge gaps. And in this particular picture, this is an acrylic retained device, and they're showing these huge gaps already in that, even though it was installed intra-orally. I would say that probably the zirconia frameworks would be a lot more inaccurate than that, and would cause all kinds of micro gaps, probably 100% of the time. And here in this other diagram, we see one of the macro gaps. Again, this macro gap is huge. I would quickly estimate it to be over 150 microns or so in size, and both these implants in the anterior show bone loss. The other implant is not exactly in the same angle as the one beside it. I'm not sure if there's a macro gap there or not. And so those are my comments on that particular. How do they actually detect the macro gaps? I think their system of detection was probably fairly coarse. And however, when I take their a logarithm and I feed in different parameters, for example, history of periodontitis, if I feed that in and I feed in lack of passive fit, right away the patient with only those two parameters and a milled prosthesis will already be in high risk for developing peri-implantitis. And you can see here the high risk group, the recommended recare program is 3 months. And as soon as we add one other factor, for example, the existence of plaque, and how many of our patients don't have plaque, and or add on a little bit of bleeding on probing, well then right away we become in a very high risk group, and he's recommending a 2-month recall program. Now my problem with all this is that how do you actually diagnose the macro gap consistently, and how do you maintain a macro gap? How do you clean it out? Even if you see it, how do you clean it out? And if it causes bone loss, how do you treat it? See, it's very difficult to treat an implant abutment misfit. And if one doesn't take away the cause of the problem, then it's difficult to treat effectively. If you put a bone graft there, well, it's probably going to melt away because you haven't corrected the underlying problem. So P.I. Braunemark was thinking about this in 1985 already, and he was hoping that technology would allow him to use models that were perhaps in the 10 micron range in inaccuracy. And I would say that as a bacteriology background, a 1 micron diameter or less, that would consider a 10 micron sloppy fit would probably still be considered sloppy on the bacterial level. However, today's models are probably plus and minus 100 to 250 microns at best. And when you get a model, you don't know how accurate it is. We cannot clinically assess it, and that's a big problem. It's like a hit and miss thing. So I think the safest thing to do is assume that it's inaccurate and develop our treatment plans with that assumption. It's sort of like when I worked on the railway. If we can't see the light, we assume it's red. We don't assume it's green and just go and complete things. So that's where we got it. And if we have inaccurate models like we do, what results is mechanical and biological instability of the joints at the implant abutment junction, which is deep and hidden. And the bacteria have no problem with their long flagella and motility to get in there and attack the surrounding tissues from that point. When we go to multiple screwed-in prosthetics, that just amplifies the whole problem. And Carl Misch was all over that in both of his 2005 and 2015 textbooks on the subject. He was all over it. And you should know that you have a misfit when the installation technique proposes that you have a specific screw tightening sequence to try to force the joints together. And the literature is full of this misfit. I'm not inventing it. I'm not making this stuff up. In fact, Derricks et al. In 2016, they did a huge study on the Swedish population and the effectiveness of implant treatment and prevalence of peri-implantitis. And our Royal College was so incensed by this paper that they decided to send out 9,000 copies to all the dentists in Ontario to tell them we better start telling our patients about the prevalence of peri-implantitis. And but I'll talk about that. But patients in their study with 4 or more implants were 15 times more likely to have peri-implantitis. Now, that tells you something. And 77% of their prosthetics were placed in by a screw-in technique. Just so we can't blame it always on the cemented-in prosthetics. Yes, and but their study also showed a very high prevalence of peri-implant disease. That's a combination, of course, mucositis and peri-implantitis. And I reviewed this paper several times and wrote a little editorial because I think, unfortunately, this study exaggerated the prevalence of peri-implantitis, and I would expect an exaggerated prevalence because, unfortunately, I think the post-treatment care of their patients was wholly inadequate. And I invite you to go onto my website and read my editorial on that basis to see if you agree. In any case, in their as a conclusions or the recommendations from this paper, they recommend that they state that peri-implantitis or peri-implant disease is a common complication, and therefore we really should be talking about it with our patients before we start the treatment, so they're not surprised after with the problems that they have. And they also recommended clinical strategies that should include preventative measures. And well, who can disagree with that? But one of their prevention methods or clinical measures is that we should, as clinicians, be preventing peri-implantitis by managing peri-implant mucositis. Now, that doesn't sound like primary prevention to me. It doesn't sound like, and how do you manage mucositis caused by macrogaps or implant abutment misfits? It's very difficult. It's very difficult unless you get the tissue to shrink beyond that connection, and then perhaps you can manage or stabilize the condition. But otherwise, it's very difficult to fix an implant abutment misfit or macrogap. And however, this misfit or macrogap can be totally prevented by intra-oral cementation. Now, how is that possible? Well, the way we receive our custom abutments or abutments, the connection between the implant and the abutment is actually pre-milled. It does not depend on our impression techniques or manufacturing techniques or customization of our abutment. It doesn't depend on that. So if we're able to put our abutments in individually, like I'm showing in this case, well, we can optimize the implant abutment junction. So at least we're starting off with a minimal misfit at this junction. And also, when we do that, we don't have contacts, tight contacts, holding us off the base as we're trying to put it in, put the abutment in, and we also have the best visibility ever. We can't see the joint very well, we don't see it at all, but at least the other conditions are present. Can you imagine doing the whole thing when it's already connected to the prosthesis? It makes that job much more difficult, even if we forget about the model inaccuracy. So that's how we can optimize the implant abutment junction. And of course, the prosthesis is still inaccurate because it's been produced on a model from our impressions. But at least now we can adjust it. It's a lot easier to adjust. And if it binds on the implants, we can adjust even the inside. And there is a cement space that gives a little tolerance to the system. So when we cement it in, we can create almost a passive fit over the top of these abutments. But of course, we have a problem too, and the problem is residual subgingival cement. And I want to talk about that next. But let's look at this. These are my diagrams again. Again, the prosthesis and the abutments have been created or assembled on a model, but in this time the prosthesis has not been attached to the abutments, and we have a significant cement space between the two elements. So now we take the abutments out, change the abutment screw for a new one, and we can optimize the implant abutment junction. That's big. Now we can control at least that joint every time, not just dependent on how bad the inaccuracy of the model is. We can optimize that. We've controlled that variable. And now the cement space gives us a little bit of leeway to, we still have to adjust the contact occlusion and fit, and then we cement it in. But of course, we have some problems with the cement getting under the tissues. And I'm going to talk about that later. So what do I perceive to be the actual prosthesis installation dilemma? Well, the dilemma is that many cementers deny having this serious problem. Yes, and I was one of those because for 20 years I used stock abutments and I depended on the contours of my prosthesis to give me the emergence profile. I didn't understand why one would spend extra money on a custom abutment. Now I use custom abutments, but I would have denied that I have the problem because I'm very careful, and many cementers still deny having this problem today. And the screwers, oh wow, they all they look at is the residual subgingival cement and the problem that can cause. Now they have an excuse to forget about the implant abutment misfit that they're creating. And they need to focus back on that problem because it's a serious problem. It's a blind alley that they've run up, and they got to stop doing that. And that's the long and the short. And the screwers, they never talk about the Nissan at all long-term outcome of cemented versus screw-retained implant-supported partial restorations. They never talk about that study. It's a great study. But and it was done a number of years ago. Well, 2011, it was the report. Mean follow-up time, 5 years to 15 years. And here's what they found. They found that screw-retained restorations had 4 times, 10 times the amount of ceramic screw fracture, because at that time they used a lot of porcelain bonded to metal crowns and bridges, and when you leave a hole there for screw access, that ceramic is unsupported and gets fractured like 10 times more than with cemented restorations. And now a lot of this has been corrected because many people in the posterior use zirconia. So we try to avoid ceramic in the posterior, but that you could see what that screw hole did. What about abutment screw loosening? Well, the screwed-in technique caused 3 times more screw loosening than the cemented restorations. And I think the 9% rate is a bit high, considering perhaps that they used porcelain bonded to metal, which might have made these prostheses and parts maybe a little bit more inaccurate. It's a little high, but it's certainly 1/3 of what the rate was with the screwed in. So I would suggest there's a significant macro gap here, even with these 2 to 3 unit bridges that were being used. This is not like all on 4. This is smaller units. And the mean gingival index, well, the screwed-in restorations had 5 times more mucositis than the cement-in prostheses, and they had double the amount of bone loss. You see, so the screwed-in prosthesis advocates do not refer to this paper. In fact, I was surprised listening to all the sessions on peri-implantitis from Dr. Charles Goodacre and also from Mark Lynn, that both of them never even mentioned macro gap, but they showed pictures of residual subgingival cement. So you know what, maybe they feel that it's not such a big problem, but I think we have to readjust our thinking here and recognize that it's not only a huge problem, but it's a blind alley that you run down that you can't recover from. And I hope today's talk will focus on that, focus you on that. So the one paper that many people refer to, the screwers especially, is that this paper by Thomas Wilson, and it was a small paper, but very potent and very well done. And Thomas Wilson is a periodontist and I guess doctors refer uh, um, their persistent mucositis, periimplantitis problems cases to him, and when he took an endoscope and he looked at 39 consecutive patients with 42 implants with single teeth cemented crowns. And he took an endoscope and he looked down and he found 81% of these cemented single crowns had a residual subgingival cement. And when he cleaned it out with the endoscope or by raising a flap, 74% of them got better. And that's pretty amazing because unlike the macro gap that you can't fix, if you just remove the residual subgingival cement that you left behind, well, 74% of them will get better. I think that's a better prognosis for sure. And if we look at the two numbers, 74% times 81%, that makes 60%. So my hypothesis was that if you could prevent the cement from going there in the first place, and you prevented the macro gap, well, then you could probably reduce your complication rate by 60%. And so, I'm just reiterating here, 74% of the cases got better, and that's a lot better than we can expect from other technologies. And now, Albert Einstein says intellectuals solve problems and geniuses prevent them. Well, yes, if we can only prevent the cement from going subgingivally and we can prevent the macro gap, well, we certainly could reduce our complications by 60%. And I would say trying to manage mucositis to prevent periimplantitis is sort of intellectuals trying to solve problems, and trying to prevent the cement from going in the first place would be geniosity, and I think we should be geniuses and try to fix that, because treatment complications are very expensive for our patients and for us. So what do we understand about intraoral cementation today? Well, first thing we have to understand is that it's a hydraulic event. And hydraulics is a whole different world. And that's why I hired Vladimir to help me navigate that world a little bit. But anyway, what do we know about excess cement? We know it can be difficult to control. We know it can go deep into the subgingival environment. We know it can be difficult to remove and detect. And we know it's a risk factor for periodontitis and periimplantitis. And we know it can be removed after surgical access or by endoscopic means like Wilson. And so what determined the margin designs that we've been using for so long anyway? Like, who determined those margin designs? Well, the first margin designs were made on stock crowns. So the dentist would have a whole drawer full of stock crowns, and just like our stainless steel crowns in our pedo patients today, in our children patients today, you would try to find a crown that would fit well enough and adjust it a little bit, and then we could put cement in there and cement it in, and then we could burnish the margins against the tooth, and if we burnish the margins well enough, then we would reduce or delay the washout of the cement that we used to put it in, and that's what determined the feather margin. Nobody ever thought about cement being a hydraulic event and how it interact with the gingiva before, you see. And the same thing after with the chamfer and butt. Nobody ever thought about gingiva, but like, what percentage of your patients have gingiva? And what percentage of the gingiva interacts with your subgingival margin? Yeah, so nobody ever really looked at that before, and I mean, that's surprising, because they certainly did a lot of studies on cement. And older cements, of course, like the zinc phosphates and the polycarboxylates, well, the thing was they didn't have a lot of compressive strength. So during installation, you had to keep your cement spaces really small so they wouldn't wash out so easy, and certainly your marginal fits had to be quite good so they didn't wash out so easily. And so the cementation process became a very high pressure event. In fact, there was a study where they estimated that it was 40 Newton centimeter was the amount of average force put for cementing a single crown. That's like 4 kilograms. Yeah, so the use of the cement, the type of cement, and when you start widening the cement space, the properties of the zinc phosphate and polycarboxylate change dramatically. You know, they become much more soluble, and they're much less able to withstand compressive strength. So we really need to look towards cements that have higher compressive strength and less solubility. But we'll talk about that a little bit later. So my first experiment, I went to a local machine shop, and they made these aluminum posts, and I used a cement that didn't flow that dramatically that you could see, and I made these zirconia crowns with different margin designs to match the posts. And what we're going to look at here is the effect of margin design on cement flow. And as you can see here, here's your feather margin, and the cement's coming out of the crown, and all the cement is going down. And then if we go on and we look at the chamfer, well, we kind of expect the same thing, because the margins of the crown and the margin of the retainer are all face downward, so it's going to go down. And here's the inflected margin that I came up with at an American Academy of Implant Dentistry annual meeting in Phoenix after the Pinero talk, and it's an inflected margin, and it redirects the cement up. And that's the thing on margin design. So I don't understand why we want to continue to use this once we know about this one. The only times I think we could use such a margin is if the dimensions of the teeth we're replacing are very small, and if we have to put those margins subgingival, perhaps we should buy an endoscope, and so we can take out the cement or raise a flap and clean it out, because there's no way you're going to be able to control the cement. So I would suggest that whenever possible, let's move to an inflected margin, at least that can redirect the cement upwards rather than downwards. As I'm trying to develop the project on the effect of margin design, I took some models, and I put a soft tissue model, and I wanted to take x-rays of this process and show how my new margin would prevent cement from going subgingival. But lo and behold, that didn't happen. It didn't happen. And indeed, in every single case, the cement went way subgingival. And I didn't understand what was happening, and it really was unexpected. And so I had to go home and ponder the situation. And then I realized the difference was that there was some gingiva in place, and the gingiva was causing some problem. And so I had to go back and I did some experiments again. This time I created a Tygon tubing gingiva that would interact with the base of the crown prior to the crown being seated, and that would be like what we find in the mouth. So here we go, and here's the experiment. I put the crown in, and I'm watching what's happening, and I can see that the crown is starting to, the cement's coming out, being deflected, and then I see as I push the crown beyond the marginal position, the cement really starts going way past the margin. And I tried this now with the chamfer, because I have 3 different margin designs here with the chamfer, and guess what? That same thing happens, just like on the other model, and it looks like it's going a lot further, but you'll see the other one really went quite far as well. And then I tried with my beautiful reverse margin, my inflected margin, and lo and behold, the same thing happens again. So the gingival effects are really quite huge. They're really quite huge, and way beyond anything I could see. And you can see even the cement is being drawn down further as time goes on. And as I spin these around so you can see better the extent of the cement, wow, could you expect that the cement would go down that far? So I was able to identify actually that the gingival effects were made up of at least 4 effects, which was deflection, the gingiva deflecting the cement as as the cement touched it during the intraoral cementation process, and then an eddy effect as the cement hit itself it caused a little bit of a vortex, a low pressure effect, and then the eddy effect or the plunger effect, that the force of the crown itself pushing the cement down really pushed the cement forward. And then the real other surprise was the bellows effect, where as the side of the crown pushed the gingiva aside, it creates space. It creates space between the implant abutment and the gingiva, and this actually causes a sucking effect. It causes the cement to be sucked a lot further down than one would expect otherwise. And so now that's how the cement gets there in spite of best efforts. And the worst is where we have skinny abutments with fat crowns. And we need to know why, is because if we depend on our crown to do the emergence profile, because we want to use stock abutments, and we want to take that from there, what's going to happen is the crown is going to touch the gingiva first, and it's going to create a seal which prevents the cement from escaping from the subtissue, from the gingival, from below, from the subgingival environment. And when we do that, we're going to create the gingival effects, and the cement's going to go into places where we can't get it. So we got to stop using stock abutments. We need abutments that take the shape of the crown, of the base of the crown, that push the gingiva out of the way, that allow the crown shape then to let the cement out. And that's what we need to do. And unfortunately, that's going to require a little bit of change in the way we do things. But that's what's necessary. And I think a lot of prosthodontists, like Wadhwani and people with a lot of experience in this area, they understand that you need to use custom abutments. And I'll go further, that you need to use well-designed custom abutments. And I've spoken about them when I introduced the gingival effects. And they have to be well-designed because they have to mitigate the gingival effects. And that's so what good is a problem without a solution? Well, you see, this is the normal crown design again, and we know what's going to happen here. We're going to stimulate the gingival effects because the crown is wider than the gingiva, and it's going to trap the cement. You see, in this case, the cement didn't even come up. It was totally trapped. And I can tell you, when even half of it's trapped, it causes a problem. Well, the second crown here that we just observed is narrower than the gingiva. And so as soon as we do that, we mitigate the gingival effects because now the cement can come up. And that last crown is a hybrid crown. So the part of the crown that interacts with the retainer is narrower than the gingiva. And so again, just like the narrow crown, it lets the cement up, and you can see that's it. And in the diagram here on the right side, you can see that little inflection in the subgingival portion of the prosthesis works together with the well-designed custom abutment to cause the cement to flow up and out of the tissues, and also gives us a little ledge against which the clinician can easily clean up, and the margin of the interface between the crown or the prosthesis and the abutment is never facing downwards towards the tissue, and I really like that as well. So those are my three experiments that showed the relevance of well-designed custom abutments and well-designed prostheses for mitigating the gingival effects and controlling the cement. They're part of the cement control system. There are other parts. But I would be remiss if I didn't speak about the retainer replica technique. And the venting technique is very similar to that. And it was invented by Pinheiro and Wadhwani in 2009. And in 2009, I guess, they try to figure ways to reduce the amount of cement that gets down there. But you see, it's not the amount of cement that's subgingival, is that any cement goes subgingival. And when you try to mitigate the problem by reducing cement, then you run into the other problem, creation of voids where the cement does not really fill the entire crown. And I think that's even a bigger problem than subgingival cement, because you can't raise a flap and clean out a void. It's even hard to detect a void because it can be a relatively microscopic event. But I can tell you, when the bacteria get in there, they can create gingival problems, and that's the problem. And you can't recover from it again. So voids are, I would suggest, in the subgingival environment, are worse than anything. At least if there's residual subgingival cement, you can raise the flap and clean it out. All the other ones are blind alleys again. And doing the balance act like this elephant on a ball, I mean, he's pretty well balanced, but even in an in vitro situation, you can't do it. You can't do just enough cement so you don't get voids or overfill. And if you get a little bit of overfill, it's really difficult to find and clean away by the clinician. And if you get voids, you're dead. It's a fatal error. And the bacteria with their little flagellas, they find these little spaces and they'll populate it, and they'll have parties, and they'll grow big families and create big problems for your patients and for you, because they don't like problems and they don't like you to create problems for them. So, and with the flow of cement out of a crown, just a slight angulation difference during the insertion of crown can cause the cement to go preferentially in one direction or other, or even a little bit difference in roughness on the inside of the margin of the crown can do a similar thing. So you cannot control that. Forget about this system. It doesn't work, and it's dangerous. And here's an experiment I've tried to replicate the Wadhwani Pinheiro system, and you can see I've used Teflon as a spacer to leave space for cement, but there's no stops there, so one could not expect that we're really controlling the thickness of cement in the first place. And this is the way this is called the ice cream cone technique. I put a little bit of cement on top of the retainer, and I put the cement on the occlusal surface. Well, I undershot the amount of cement I needed. So once you're starting to try to put just enough cement, you're going to get trapped. You're not going to put enough cement, and you can't see. So here I added more cement. Now I got enough cement. Now I'm squeezing out the cement. And you see, there's enough pressure under there that when you lift it, the cement causes some recoil, as well as this rubber, this silicone causes recoil, and we get a little air. But look at how irregular the cement is on the inside of the crown. So here I'm wiping it off, and now I'm going to put it on the retainer. Again, you're going to see all kinds of voids or irregularities in the cementation. Take a look at it. You know, like these clear areas are where you have thin cement, and just look. And here we ran out of cement before we seated the crown. That's a big problem, because we just try to put just enough. We use this technique. We're just shooting. We're just working blind. We just don't know. And you're not working with crowns that you can see through like I do. And look at where we have excess cement, we have no voids, and where we have not enough cement, we have voids. And that was Milan's finger. He was pointing out another big void. And the cement's getting hard, and you can see I pushed down and expressed a little bit of more air, but we ended up with a void. And that's just what you don't want to do. And if you put more cement in, well, of course, then you have excess cement. So you got the original problem. If you don't put enough there, you'll have a hard time finding it. You know, when you put a lot there, cement likes to stick to itself. And so see here, you can see a direct continuity between the outside of the retainer and the void. I guess nobody really would like to have fungus and bacteria growing in there. And here you have excess cement, you have no voids, and here's another little void we didn't even see. So that's the problem with this implant replica technique. And where I started getting upset about this whole thing is that it was not only with Wani's paper, but a paper where Coyce and his colleagues also published on it, just a slight variation of the material of the implant replica technique. And then I see people in different parts of the world replicating that. It's really not a good system. And I was a little disappointed when both Wadhwani and Coyce, who are both prosthodontists, when they talked about the purpose of cementation, they both only mentioned retention and not that the cement was there to fill space or prevent voids. And I think that's a really dangerous thing, to leave voids there. And when the cement washes out of the prosthetics on natural teeth, it creates a void that is that causes that allows the bacteria to enter and incubate and cause caries, periodontitis, endodontic problems, and it causes the top 3 reasons prostheses fail. After 10 years, it's the magic failure rate. After 10 years, when you see the big caries around these prosthetics, and with implants we don't get the caries, but we certainly get the peri-implantitis. So we need to prevent voids, and it's a breeding ground for pathogens. And if you have voids under facings and crowns that you can see through, you might see a discoloration of your crowns. I would suspect voids, and certainly they can stink and taste bad, because we had plenty of experience with the early Branamark that had Branamark stuff that was not precisely milled and mated, and they stunk to high heaven. And that's what happens with voids. So we have to prevent those. I'm writing a little paper showing that a slight angulation, angled force on installing a crown will cause excess on the side opposite the force. And so if you just had a little bit less cement here, you'd have voids on this side and excess on this side, and you'd be creating problems. And they're very difficult to detect. You have to prevent them. And so over failure prosthesis with cement, don't allow air. Like imagine how you're going to expel the air, and firmly hold the prosthesis down while the cement sets, and try to put it in slower so you don't get so much pressure buildup in the cement underneath your prosthesis, so it doesn't tend to lift when you just let go a little bit, because otherwise what will happen, the crown will lift a little bit and it'll suck up tissue fluids in under the crown during your cementation process. So that's why I like low pressure cementation, and we'll talk about in a second. Here's my study on amount of pressure. Remember, I told you 4 kilograms of pressure for cementing single crowns. And here I've zeroed the scale, and I fit the bridge, and with an 80 to 100 micron cement gap in order to allow the cement to flow out freely. And with acrylic cements, that does not depreciate does not reduce the compressive properties of the cement, and it doesn't dissolve out at the margins like your other cements. And you can see I got up to, when I'm holding it in, I'm getting up to about 107 or 109 grams of force. That's like 40 times less than 4 kilograms of force. And so when you increase your cement space, you can reduce your cementation pressure, put the cement in such a way, use excess cement, and then you'll not have so much pressure underneath your crowns. And then harden it. Start hardening it before you release your pressure. So those are the ways we prevent voids, reduce our pressure to get more control of our cement. Now, clinical experiment number 1 is just, first I want to point out here, when I receive my crown and my abutment and my model, this is a printed model, I receive it sterilized. If there are cemented components in there, you can't sterilize it because it degrades the cement. The heat degrades the cement. But if I don't assemble it, have it assembled, then I can do that. And it seems that the models can withstand the sterilization procedure, and that's good. And so anyway, here's a case. The original abutment screw cover screw got loose. It got lost, so I made it a custom-made one. It's nice to have your own lab to be able to do that. And then I created a custom abutment with a reverse margin. All these margins are predetermined in terms of their height, and the inflection of the margin will redirect the cement. And here's your zirconia crown, crown. And here's how it looks in the mouth. And here I'm using Teflon, which has also been sterilized, to put in there. And when I put the crown down and I just harden this a little bit for a couple seconds with my light, it's so easy to remove the cement. And because the margins are higher, it just gives you so much more control. So I highly recommend this system, and it's so easy to clean out and get a consistent result. It shouldn't be a crapshoot whether you are going to get the cement out or get it down or create a void or create a micro gap or not. It shouldn't be a crapshoot. It should be a home run every time, and this will give you a home run. And it doesn't matter what the material, whether it's a hybrid abutment that you're going to be cementing over, or whether it's going to be a titanium abutment. I'm usually using titanium, but I have no problem with the hybrid abutments. They just have to be custom abutments. And you see the cement in this case, another acrylic-based cement, just so easy to remove and get a nice result. And I've done over 600, I've restored over 600 implants already. I have to wait some time before I assess the rate of problems, of course. I'm wishing that some university that's forward-thinking will pick up on this project and do the appropriate clinical trials. I'm not set up for it, and I shouldn't have to do it. It should be done by a university, and I hope that'll happen soon. Because I think reducing our peri-implantitis rate or peri-implant disease rate by 60% is a good goal, and I don't see anything else out there that even comes close to that sort of a reduction in peri-implant disease. So universities should be protecting the public and should be working on projects such as this. This is very innovative research that I'm sharing with you, and I just can't do it all alone. I need the help of the big powers to be here. In any case, here we go. Here's one of my experiments. I got Milan to make 2 crowns on 2 custom abutments, and one with a hole in it with a little bit of blue acrylic. That's the screw axis hole. And then I basically cemented this one first, and then I cleaned away the cement, and then I took it out. I just drilled through the screw axis hole, unscrewed it, and then I could examine whether any cement is getting past the edge. And then after I finished that, I put the real crown in without the axis hole, because I don't want to have to deal with maintaining a screw axis hole, especially on the occlusal surface of a molar. And so then I cemented in, and if this one's going to be good, I'm pretty sure this one will be good too. And so far, I haven't found one that would let me believe that I'm not controlling the cement. And so here we go. We take off our cover screw, put our abutment. Yes, the margins are a little high. Why would you even want to go subgingival in the posterior anyway? If you inform your patient that it's better from a biological point of view to use something like solid zirconia and to use supragingival margins or equigingival margins, I can tell you 9 times or 9.5 times out of 10, they're going to choose for biology and mechanics over hiding a margin in the posterior. There are some cases that'll need you to do that, so then you have to go a bit more subgingival, and or you might want to change to a hybrid abutment if the aesthetics are that important. But anyway, here we go. Put the Teflon in, glue in this crown, clean away the cement. It's so easy to do. And then put the regular crown, and then take out the one with the hole in it. And here you can see the X-rays. I was able to clean the cement away very nicely. And here is the one I removed with the hole. You see the hole here. And I used a little water on a Q-tip just to clean away the saliva proteins, because they hide the view a little bit, and you can see there's absolutely no cement beyond the margin. And this happens every time. Every time. It's so easy, predictable, and I've optimized my implant abutment junction and controlled cement, so I expect 60% less. At least I've removed the dentist-caused problems from the installation procedure. So my liability will be a lot less, and my patients should be a lot happier if they were able to reduce their peri-implant disease and complication rates by even half or 60%, that's even beyond imagination what that is. So here is experiment number 6. I just put 2 of them together. This was a really huge case I was working on, but I put 2 of them together again. I just made blue acrylic screw axis holes, cemented it in, drilled them out again, and then assessed how it looked underneath. And I got to point out now, because I'm going to be talking about it later, that you see, it doesn't matter if I cemented this in, and it looks a lot like a screw-in technique, doesn't it? But because I cemented in, I've optimized my implant abutment junction. I've controlled my cement, and now I can take it out if I want. Here I glue it in. How long does it take me to drill a screw axis hole through the top of zirconia? Like 3 minutes? What are we talking about? We're not saving a lot of time, and I bet you it takes me a lot more 3 minutes to maintain these screw axis holes that we seem to want to do. So anyway, here we go. As long as our implants are parallel, it'll come in and out pretty easily. There we go. And here, when we look underneath, no cement beyond the margins. That's it. No cement beyond the margins. We have an optimized implant abutment fit. And look at here, for a case with where I'm splinting 2 implants together, it's no problem using engaging abutments. I don't have to use the lesser multi-unit abutments here. So that's good too. So I'm going to get a more stable joint and less screw loose. In this version, the experiment 7, I just left the cement behind because I wanted to see and fit it together to see how it kind of looks. You see, I picked up this piece here and I put it over here just to see how it looks like. No cement beyond the margins. Custom abutment, you can see how complicated that contours the height of the custom abutment is. The well-designed custom abutment controls the height of the margin, and it can put it where you want it. Like, do you really need to be subgingival interproximally ever? Maybe in the anterior, but not in the posterior, not on the bottom in the posterior. You never have to go under. So you need a custom abutment to do that. You can't do that with a stock abutment. And even if part of the gingival effects will work over a very small space, a very small distance. So you might have everything set up nice with your stock abutment with an expensive contour on it, but if it's not right all the way around the tooth, you're not going to be able to control your cement. So you need a site-specific, well-designed custom abutment to do this process. So now I wanted to see, in this version, experiment 8, I wanted to see whether I could reproduce the residual subgingival cement in vivo. And so I got my lab technician at Milan to grind a stock abutment like I did for 20 years. And then he created a crown. Unfortunately, he put my inflected, my cement release valve design into the crown, so we had to fill that in with acrylic to go on with the experiment. I pushed the crowns into place with high pressure because I'm trying to overcome contacts and also overcome the gingiva in this case. And you can see here, residual subgingival cement, residual subgingival cement, residual subgingival cement. We cannot control cement with this sort of design because we violated the gingival effects. The gingival effects came into play and took the cement beyond where we thought we should have been. And when we have really tight gingiva like this, you know, do you like to put your fat scaler under there and rip away some of that gingiva? That's maybe one of the reasons people don't go down there that much. And the second thing I realized from this series of experiments was that it's not really the residual subgingival cement that maybe moved our referral-based practices away from intraoral cementation, because this can also cause open margins, and those open margins are visible quite often on x-rays, and they're really not good for business, and they're not good for our patients either. So I realized this gingiva not only causes problems with residual subgingival cement by stimulating the gingival effects, but it also can result in open margins. And so do tight contacts result in open margins. So do really small cement spaces required with other cements. So these are three things, and I'll come out with something on that information later, but be alert that it's a problem. And then so now I switch to a beautifully well-designed site-specific, well-designed abutment. I put it in, I can cement. I've controlled the cement really well. And so to summarize the cement control system, or a way of controlling the cement and optimizing the implant abutment fit, we could say that we can prevent implant abutment misfits and macro gaps by avoiding the current screw-in techniques that assemble the prostheses on an inaccurate model. I think that's a pretty good statement to make, and unfortunately it's going to cause a lot of anguish out there. And the second thing is, if we want to prevent residual subgingival cement, you have to avoid poorly designed custom abutments, and there are lots of them out there, expensive ones that are not designed with mitigating the gingival effects in mind. And of course, stock abutments, stock abutment prosthesis combinations where you depend on your prosthesis to do the emergent profile for your crown or prosthesis, and are not sensitive to gingival effects, are going to cause residual subgingival cement. And if we want to prevent cement voids, really you should be avoiding already cements that wash out at the margins, because once they wash out, they will cause a void. And avoid trapping air under your prosthesis during the cementation process. In one of the renditions of the Wadhwani paper, he was suggesting putting cement on the cervical third of the crown prior to cementation, and he showed beautifully how the cement would rise up, but trapping all that air would make me really nervous. So I highly recommend you put your cement just under the occlusal surface, like fill the crown from the occlusal surface down, and imagine how the cement's going to be expelled. And avoid cement minimization techniques. Even venting techniques can get you to lose control of the volume that you actually have in your crown. So I would avoid those techniques. And I would suggest to you that if you use a little bit a bigger cement space in acrylic cements like Reliance Ultimate or Unicem, and there are many others, then they won't dissolve out and create voids that way, and you'll be able to cement your prostheses in with a lot less pressure, and their ability to resist occlusal loads with their compressive strength won't degrade over 100 micron space. I think they start degrading, the properties start degrading after 250 microns, and that's not even within what I'm recommending. So the question is, why do some clinicians choose to use screw-in installation techniques? Why do they do that? And I would say probably the biggest reason and the most valid reason is that they believe that they need to have retrievability, so they can take things out after they put them in and modify them, or there are a lot of reasons. Maybe unfortunately retrievability creates problems, right? But and some answer, which I thought was not a very good answer, was because we can, because it assumes that adding retrievability features, it really is free, when it's not free of cost or risk. So that's kind of a lame answer. So I would suggest not to use that answer anymore, because especially not to me. And I would say probably one of the reasons is, especially for referral-based practices like prosthodontic offices and implantologists and people who install crowns and bridges, is that I think many got frustrated with by open margins, especially, but they don't look good. They're not good for business. And even if you could, you can't, once the margins open and the cement's set, like it's difficult to fix, right? You've got to cut it off and start over again. And if you don't really understand the intra-oral cementation process, it's just going to happen again, and it's going to happen too often, and that's not good. and then of course residual subgingival cement. I think that gave them more of an excuse to move away from intraoral cementation rather than being the primary stimulus. But who knows? Depends, I guess, when they started having a problem. So one point I want to make out is that what my experiments showed me is that retrievability is not specific to the screw-in technique. It's specific to, it's a result of retrievability features. Features like, and I'm going to cover those, but features like parallel arrangement implants and a working path of insertion. It's not, it has nothing to do with whether you cement or screw in your crown. Now, you can't screw in your crown if it's not going to be retrievable, and you certainly can have more versatility with the screw, with the cement in, because you can cement in whether it's retrievable or not. So I guess you have more versatility for cementation, but it has to be pretty well retrievable if you want to screw it in. So there you go with that. But let's look at these retrievability features. And I think the first and most important retrievability feature that you have to plan for and put into your treatment if you want to make something retrievable is you need to have a working path of insertion. And that usually means you need to have your implants relatively parallel. And your path of insertion has to be sensitive to adjacent teeth and implant prosthetics, right? And so one of the things, in order to get such a working path of insertion, when you do a big multiple case, you might need to use a guide of some sort. These were put in freehand. I don't need a guide for 1, 2, and 3 implants. I can make them parallel enough, but not everybody has that experience, so I'm not sure where you are on that. And can we really make them absolutely parallel? Well, the answer really is no. And the literature supports my answer here, and because it's a 3-dimensional space issue, and it's very difficult to make it absolutely parallel and without any twist in it and stuff like that. So no, you can't. And as a result of that no answer, we have to use multiple unit abutments to give just a little bit of tolerance to the system so you can get them in. So I'm suggesting to you that maybe for 1 or 2 implants where you're purposely making them relatively parallel, you might be able to use an engaging regular stock abutment. I mean regular abutment. I'm not a proponent of stock abutments at all, but a regular, say, abutment with an engaging feature. Rather than these, I think these multi-unit abutments, they do not engage very well at all, and I think it may be because of the number of units that are in play. Maybe they work off each other, and they'll make you feel like maybe you have a better fit. They fool you more that you have a better fit, but I think they're just a necessity of the system, the way it's set up. If you need to have retrievability, then you're going to run into requiring those. Are they more stable? I don't think so. Now, the feature 3 has to do with somebody's invention that Nobel Pharma calls angled screw channel abutment. And you know what? I really like that that invention. I think it's cool because it gives the clinician a little bit of control of the angle of the channel, or where the screw access hole is going to be, if you want to create some retrievability for your prosthesis. And it's good. And a number of other companies now carry it in Europe. It's not just Nobel Pharma. And also, especially in the anterior, by having this angled screw channel, a screw access hole, I think it reduces the amount of cantilever that you have to use, and so that makes the mechanical fitness of your prosthesis better and make it easier to clean. So I really like those features. Unfortunately, if you're going to assemble the prostheses on an inaccurate model, you're going to run into all the problems of the screw-in. It doesn't solve the screw-in implant abutment misfit problem at all. You know, it doesn't do that. So, but again, you could use this with a cementation device installation system easily, and then you'll know where your screw access hole. You could always make your default if you want to use this such a installation technique, you can always make your default out in the center of your prosthesis, and I think that's pretty cool. But it doesn't solve all the problems that the screw-in system has inherent to it. So here's an example of a case where retrievability adds cost and risk. Well, here this guy's a smoker. He's not really that healthy. He's pretty old. He lets things go quite far. He's got a big problem. Good thing he has lots of money. And so here we go. So this case right here, I really was not comfortable doing a sinus graft with a young healthy person. I probably would have done a sinus graft if they would want to take the risk. But anyway, so let's look. If we wanted to make our prostheses, and here in this case a single crown retrievable, I think we'd have to do a sinus graft and do an implant here, and then we do another single implant here, and leave this guy alone. That's certainly a treatment. So this graft costs money, and it adds risks to the treatment, especially since he's not healthy, not that healthy. And by just taking out this between tooth and putting an angled implant in there, which makes it non-retrievable, we were able to go into native bone, and that would give us a higher success rate, I imagine. And then we didn't need to require the lateral sinus graft. And here's how the prosthesis looks on the model, and it was adjusted and cemented in. You can see the profile of it. And this is how it looks in the mouth, and it's not quite done here yet. And there we go. So I just want to bring to your attention that retrievability features are not free. They add risk and cost treatment. In the anterior, what they do is they have to start doing grafts in the anterior to upright your implants. In the posterior, you have to do sinus grafts and other maneuvers. So site development procedures add cost and treatment, and they add risk. And they might add that you might need to, if you're doing multiple units, you might need to make a guide, and that costs a little bit of money. The laboratory technology for making a retrievable prosthesis is going to cost you a little bit more money than a screw, a cemented case, because it's more normal and don't need so many fancy parts. But now, if you need screw access and you have to create cantilevers to produce it, well, if those prostheses are not maintainable, they're going to get into Palomalo's risk assessment logarithm, and they won't be able to clean the plaque away, and so you're going to be in a much higher risk. And who can clean that stuff? So you know what? It's the dentist's job to make things cleansable. It's the patient's job to clean it. And if we make things that are uncleansable, then we're putting ourselves out there, aren't we? And we shouldn't be doing that. We should see if we can run around that big problem. And current techniques, current screw-in techniques really are causing implant abutment misfit, macro gaps, and that's a really expensive problem, and we should stop doing that. Yes. Anyway, because retrievable features can be expensive, and that's it. So how about reducing the need for retrievability? Maybe when retrievability was a good idea, we had to retrieve things all the time because they were breaking down too much, and so that somehow gave us a sense of control. But perhaps if we didn't use hybrid materials and use zirconia in the frameworks, perhaps they would be more durable and we wouldn't have to take them out so much. If we wanted to control excess cement, maybe we could use the cement control system with the inflected margin and well-designed abutments and prostheses, and control cement that way. Maybe if we would optimize the implant abutment connections, the screws wouldn't get loose so often and it wouldn't distort the top of the implants. Maybe when we used smaller spans, we could use engaging abutments. And maybe if we use a double torque technique, they wouldn't. You know, just adding the torque wrench really reduced the loosening of screws quite a bit. Yes, and that's pretty important. And things like the angled screw channel maybe could reduce cantilevers if we really want retrievability. We use well-fitting parts. use night guards. And you don't have to take out a prosthesis to tighten screws. You just have to have access to the screw. And then one of the arguments for needing retrievability, well, now we can get under the prosthesis. Well, we get around teeth when we have to do surgery under there. The problem is, in both cases, if the tissues shrink, we end up with a whole bunch of food space underneath of our prosthesis. So maybe we have to redo them anyway. So retrievability features are not free. Are they worth it for the patient? You know, only the clinician and the patient have to make a decision on the value of it. And so here we have a case, a young, vigorous clinician has sold a case to this beautiful lady here, and they're going to do a retrievable prosthesis, and they're going to do all that's required to align up the implants and all those things we talked about. But can the clinician prevent the implant abutment misfit? Well, if they assemble it on the model first and put the abutment and prosthesis together in the model first, I'd say no, they can't, and they need to, but they can't do it by that old technique. So I'm proposing a Sabota modification of 1, and it's very much like the experiments I showed you earlier. So get your lab to make well-designed custom abutments and prostheses, and then get them to fill up the screw axis hole with acrylic, like a blue acrylic, so if you want to be able to see it well, and then cement it in the mouth, take away the cement, and if you want, you can then drill through the screw axis chambers, take it all apart, make sure there's no open margins or excess cement. Now here, the open margin thing, I just brought that up, yeah. That's the problem, right? So if you're going to use, for example, stock abutments in this option 1 modification, you might start running into some of the old problems of open margins again. If you left cement behind and my system wasn't working, well, when you took it out, you could take care of that and polish that edge. But if you had an open margin, well, it's a little bit more of a hassle to send it back to the lab and to get them to cook it and separate the device and hope that it doesn't break, and then re-cement it. And what makes you think it's going to go down next time? So you might run into, so if you don't use the cement control system for the intra-oral cementation technique, you might run into that problem again and again. It might frustrate you. So I recommend you use the well-designed custom abutments and prostheses. They're designed for this purpose. And Sabota modification 2, well, get the lab this time to use a white plug that looks tooth colored, and cement it in, clean out the cement and leave it there, and you'll save yourself a lot of time. And one day down the road, if you need to tighten a screw or whatever, you can easily drill through here and do what's necessary. And so that makes that retrievable. So I think that's modification 2. And modification 3 would be the simplified modification is don't get the labs to make the hole, then you don't have to manage the hole, and use the just cement it in the mouth, line up your parallel your implants the best you can, and maybe even mark your screw access holes or whatever. And if one day you get a loose screw, you can drill a hole in that particular crown and tighten the screw or change the screw. Or if you need to take it out, you can do that too. So those are the 3 modifications that are possible. And all 3 of them will optimize your implant abutment junction, which I think is really, really important. And with your smaller cumulative units, maybe you can use, maybe you don't need to use multi-unit abutments. You know what, quite frankly, I never used to. And that's the long and the short of it, because I put my abutments in individually and then I cement, and you don't have to take everything out to tighten a screw or change a screw. And so now we can prevent implant abutment misfits for retrievable prosthetics too, and this can reduce peri-implant disease by 60%. So I recommend you use those techniques to optimize the implant abutment junction and do that. It's very important. Our patients depend on us to do what we can to make them safer. So now we can provide safer treatment for our patients because we know safer intraoral cementation is the key to reducing peri-implant disease by 60%. Thank you for your attention. I'm glad you made your way all through this. I hope you'll look up some of the references that support my hypotheses and support what I'm saying. I didn't make this stuff up, but I did do the experiments, and I did discover the gingival effects and how that affects the cause of residual subgingival cement, and I also discovered how to mitigate that problem. You can communicate with me with your comments or questions at drsabota@rogers.com, and I will answer your emails. And you can also go to reversemargin.com and look at a number of articles that I've written and chase up the background to the things I told you about today, so you feel more comfortable about making the changes you need to make implant treatment safer for your patients. Thank you for your attention. Bye-bye.